Everything. Try. We have limited time. Everybody's got to talk. So I want to hear about space walks. Life on the space station. Oh, that's fun.
Hey. For the girls. Everything.
Jeremy, it's very difficult to control these astronauts. Okay, so ladies and gentlemen, welcome at Aachen University to a rather unusual event. I just said I'm happy that we don't do this every day, but only every 10 years we have a reason to celebrate like this. We have the AMS experiment on the space station. You see the astronauts standing close to it, together with Mr. Ken Bolbeck. He's sitting up there. He is the NASA AMS project manager. He helped us for 1.5 years to construct a new cooling system for the AMS experiment on the space station. We have been launched in 2011 to the space station. We have taken data for 8 years, very successfully. And now we're preparing the instrument to take data for another 10 years for the lifetime of the space station. And I'm very pleased that the NASA astronauts, who are still talking, Chris Cassidy and Jeremy Hansen, you see them on this picture. They came to Aachen in the past week to have hands-on experience on the flight hardware. The really exceptional thing is that Ambassador K. Hutchinson is here today. She is today US Ambassador to NATO, and you might wonder what our experiment has to do with NATO. And in her previous life, she was a very successful US Senator of Texas. And to get this instrument to space required a special law in the US. Flights to space are not extremely cheap. And to get an extra space shuttle flight and to pass a law through Senate requires a lot of courage and a lot of intelligence. We would not have this experiment on space station without the support of Ambassador K. Hutchinson. And I'm very happy that she made it from Brussels to Aachen to give you a welcome address. But before that, the mayor of the town Aachen has the privilege to welcome our distinguished guests in Aachen. Please, Mr. Philipp.
This is really a special occasion tonight. Dick Excellency, Ambassador Hutchinson, Professor Ting, ladies and gentlemen. At first I would like to welcome all our international guests tonight. It's really wonderful to have you all here. But I also want to welcome all of these students, unsere Studierenden hier in Aachen. Herzlich willkommen. Ich freue mich, dass das Interesse so riesengroß ist und ich glaube, es ist eine ganz besondere Gelegenheit heute, eine besondere Veranstaltung. To be honest, 8 years ago, I have to admit I tried to understand what the AMS really does and I didn't really get it till now. So everybody gets a second chance. Tonight this is my second chance and I'm really curious to learn more about it, to understand what this beautiful little Usher in space really does. 7,000 kilograms of science made in Aachen. And this is a really powerful science and research area which we are here, and we are really proud to have all this. And it's wonderful to think about what we can do next, what the next big thing, and what we can do with the ISS and do with this power here in Aachen. So welcome to all of you tonight, and I'm really glad you are here. I hope tomorrow I can say I understand. Thank you.
Mr. Phillips, thank you very much for the welcome. Ambassador, the floor is yours.
Oh, thank you so much, Professor. And it is wonderful to be able to participate in this event. As the professor said, I am the U.S. ambassador to NATO. So I am in Brussels now, and I have a wonderful German ally who is the German ambassador to NATO as well. And we provide this security umbrella for Europe and North America. That's what NATO is. And that has been a wonderful experience for me. But I have to say that my staff was very puzzled 2 weeks ago when they got this book, and it's all filled with numbers upon numbers upon numbers, and of course we're a security alliance, and they were getting ready to send it to the intelligence officers to see what kind of code might be in here. And they said, well, you have this invitation to go to Aachen and talk about the alpha magnetic spectrometer, and we're sure that you're going to say no, but we would show you this. And I looked at the invitation from Dr. Sam Ting, the Nobel laureate that you will hear from later, and this wonderful invitation, and I said, of course I'm going to go, because I had a partnership with this man, a Nobel laureate in physics, who is a rock star in our country. He's at MIT, and he came to me when I was the United States Senator, and he said, we have the most important basic science experiment that we must be in space to do. And it is the alpha magnetic spectrometer, which you see a mock-up behind you right now. And he said, we can't get the intensity of cosmic rays no matter what we would build on Earth as an accelerator of energy that can match the intensity in space. We must get this into the space station. And so I said, I am convinced. And then the NASA decided that they wanted to, instead of continuing the space shuttles that would take this to the space station, that they were going to cut back on the number of shuttles and reinvest in the next generation of shuttles, and that we would not be able to take this to the space station. So he convinced me that this was so important to find out the very basics of how matter affected the beginning of Earth and space and everything that is in the cosmos, that we went to bat and decided that we had to pass a law to add one more shuttle to our shuttle system in order to take this up. Well, it was a very long and arduous process, but I think my first thing to say to you is that if you are going to be a scientist, have the intensity and the spirit and the perseverance that Dr. Sam Ting had in knowing that this had to be, that we could not pass up the opportunity to have this learning experience. So he came to the Senate and he said, we cannot let this go. And the intensity that he had and the ability to talk in real terms to people who were not scientists and make us understand that this was an opportunity that could not be done anywhere on Earth. And so 16 countries have come together to join with our experiment, that we did pass the law, that we did then take up to the space station in 2011 to be able to document all of these cosmic rays and to learn the different types of energy. And then for the future, maybe it will be how we provide energy when Earth is growing short on energy. We don't know all the things that it will do, but I guess my big point is to say that you are students at a great university, and one that is so well respected throughout the world. And I hope that you will be also inspired to look for that next big thing, which, thank goodness, your country is investing in now. And that is going to be what he will probably talk about. But that is the next generation that will take us the next step. Germany is a lead, that's why we are in Aachen doing this. And they will be the lead for that next generation of alpha magnetic spectrometer that they're working on right now. So I'm going to say that I loved this part of what I was able to do. Today I am more in the security arena, but let me just tell you that what we're doing in space and the investment that your country, my country, and all of our allies that have contributed to the space station and to the shuttles that have gone up, and we have an astronaut today from Canada as well as America, but this is going to be part of our security umbrella as well. In NATO, we are now learning that space is being used for warfare. It's being used in positive ways to really use space to save people's lives from going into harm's way. It's also, we're using space to be able to target more clearly so that there will be fewer civilian casualties when we are in a war. But also it is for our defense, because we know that some of our adversaries are going to use space for the bad purposes, and we want to be able to deter and defend our populations by investing in the ability to know how we can keep the space from being used for warfare. So all of this is going to be so important for your future, and I love that we are committed, that Germany is committed to continuing space exploration for the good things that we can do and for the bad things that we can stop. So I want to say I'm so pleased to be here with you. I am going to have to leave, and I hate that, but I know so much of what he is doing. But I did want to have my little part of saying this is so important, and I so appreciate what the Aachen University is doing and what the country of Germany is doing in collaboration with the United States and the other countries that are involved in this space research. There are 16 of us, but also at NATO there are 29 of us that are working together for the security of Europe and North America. So we're stronger together than any of us could ever be alone, and that's what I think we must always remember for our future to be a bright one, like we hope it will be for you. Thank you.
It was a pleasure to have you in Aachen. Hope we have an opportunity to see you again. Yeah, and I understand that you have some urgent things that you have to do. So, please, goodbye. So, now we have science. And don't be scared. There are not many people on this planet who could explain the science better or more convincing. Even convincing for a senator to stand up in Senate and say, this is the experiment which needs to be on the space station, it's important. So please welcome Professor Samuel Ting, Nobel laureate from MIT, to talk about the science results from AMS. As usual, my mistake.
I have started my career in Hamburg many years ago. I used to be able to speak German. And, after being a professor at MIT for many years, you tend to forget everything. What I would like to do today is to share with you the results of the experiment of alpha magnetic spectrometer on the International Space Station. Space is the ultimate laboratory. It produces particles with energies higher than any accelerator on Earth. The physics of AMS on the space station is to study of charged cosmic rays. Charged cosmic rays have mass. They are absorbed by the 100 kilometers of Earth's atmosphere. To measure their charge and momentum require a magnetic spectrometer in space. In 8 years, AMS has collected 135 billion cosmic rays up to trillions of electron volts. We could not have done this experiment without the strong support of NASA, particularly Mr. William Gerstenmaier, who has met us, supported us, talked to us a total of 25 times. This is some of the pictures during his 25th visit. In addition, to put a particle detector on space station is very difficult, has many requirements, and to maintain the detector is a challenging thing. We acknowledge the strong support of Mr. Kirk Scheinman, the manager of the space station. It is an international collaboration with detectors constructed in Europe and Asia. There are 600 physicists who have worked together for many years in accelerator experiments. When we started, no one had any experience in space. This was the last experiment we did together. For the last 20 years, there are 3 experiments at the 27-kilometer circumference CERN Lab Accelerator. So when we started, I got this cartoon, which says it's time we face reality, my friend. We are not exactly rocket scientists. But as you can see, I don't look like them. But I want to thank the strong support of NASA JSC, Tim Baldwin, and what was acknowledged also Tara Johan, who taught us how to do experiments in space. AMS is a space version of a precision detector used in accelerators. On top is transition radiation detector, followed by 9 layers of silicon tracker, followed by electromagnetic calorimeter, 2 banks of time-of-flight counter, a magnet, a ring image chunk of counter. It was assembled at CERN under the leadership of Mr. Corrado Gargiulo, who is in the audience. It has a size of 5 meter by 4 meter by 3 meter, weighs 7.5 tons. It is a unique magnetic spectrometer in space. An electron goes through this 5 detector, leaves this trace, a positron leaves this type of trace. In 8 years, the detector has performed flawlessly. It is able to pick up 1 positron from 1 million protons, unambiguously separate positron from electron up to 1 trillion electron volt, and accurately measure all the cosmic rays to trillions of electron volt. We were able to do this with strong support from Jülich Computing Center because it provides us complete reprocessing of all the data in a very short time. The computer is the main facility for MS in Germany, provide many cores and many storage space. Let me talk about the physics. The first physics is on the origin of cosmic positons. Theoretically, the most simple explanation is protons and helium, primary cosmic nuclei, interact with interstellar media, produce positons from collisions. This must happen. And then you have pulsars, which is rotating neutron stars. A light ray interact with the pulsar strong magnetic field can produce positons. So positon from pulsars. Dark matter collision produce positons. So there are 3 possible origins. Because of its great interest, there were many measurements before MS on the electron on this axis and positron on this axis. And there are large measurements, great differences, and therefore can be explained by many theories. This is the MS measurement based on 1.9 million positron event from very low energy to 1,000 billion electron volt. The low energy part can be explained from cosmic ray collisions. The question is, what is this? And this part is the remaining pulsars or dark matter. Indeed, if you use a function to express pulsar or dark matter and plus collision, you fit the data. But in order to fit the data, you must have a cutoff. A cutoff means above this energy, positon gradually disappear. And this shows the cutoff energy is 800 GeV, which is established with a confidence of more than 0.9999. What is the possibility of positon from pulsars? Pulsars produce and accelerate positons to high energies. Pulsars do not produce antiprotons. So that is a known fact. Our result shows antiproton data shows a similar trend as positons. Antiproton cannot come from pulsars. Therefore, the positon flux most likely are not from pulsars. And then, how about positons from dark matter? What is dark matter? Why we believe there's dark matter? You can easily understand this by seeing a galaxy at the distance r, and there's a visible mass within the distance called mr, and there's a velocity, relative velocity v. In order to have a close orbit, the gravitational force and the centrifugal force must be 0. Only when you have a 0 force, you will have a close orbit. From this, you will obtain v squared is equal to gravitational constant mr divided by r. This is a measurement of galaxy M33, measurement in velocity and distances. And this is what you expect from this formula, and this is your measurement. This measurement shows a large portion of the universe is not observable. Because it's not observable, you call it dark matter. This similar trend has been observed in thousands of galaxies. Dark matter particle has a mass m. Because they're very heavy, they move slowly. Before collision, the total energy is 2m. Collision of dark matter produces many particles, such as electrons, protons, positrons, antiprotons. Conservation of energy and momentum required positron antiproton energy must be smaller than m, so there's a sharp cutoff in the spectrum at m. How quickly cut off depends on your detector resolution. So theoretically, dark matter model predicts positron spectrum with the characteristic sharp cutoff at high energies. This is a model with a mass of 1.2 TeV, including the low energy part from cosmic ray collision. So this is the model. This is all results. Compare with model. You would say this is a very good agreement. The only issue is the error is still very big. And that is why it is important to carry out this experiment to the lifetime of space station to 2024, and then the error will be smaller, much smaller, and we will have a point above 1 TeV. And the existence of this shows unambiguously we know the nature of dark matter. And then the question is the origin of electrons. This is the matter electron spectrum based on 28 million events. The contribution from cosmic ray collision is this little part, cannot explain anything. The electron flux can be described by two power laws. One power law A, another power law B, without any cutoff. So you add up these two, you will get a formula agree with the data. The issue is, what is the origin of power law A and B? So an important physics result is the electron originates from different sources than positrons. The electron spectrum comes from two power law contributions. The positron flux is the sum of the low energy part from collision cosmic ray plus a high energy part from pulsars or dark matter. The positron flux has a cutoff energy. The antiproton spectrum rules out pulsar origin of the positrons. Let's now talk about the rest of the cosmic ray. First, primary cosmic ray. Primary cosmic ray from hydrogen to ion are produced during the lifetime of stars from nuclear fusion. They are accelerated by the explosion of stars, supernova, and produce proton, helium, carbon, oxygen. This is the measurement of proton before MS. The data has rather large errors and created many theoretical speculations. This is the MS data based on 300 million events, and the data has a very small error and agree with the traditional theory up to 300 GeV, and then you have unexpected increase. That means the proton flux cannot be described by traditional theory. Before MS, there were many results on primary cosmic ray, helium, carbon, oxygen, from balloons and satellites. They are listed here. You look at all of them, they're going everywhere, and you have no trend. But when you measure this very accurately, like AMS did, surprisingly, above 60 GeV, the primary cosmic ray has identical rigidity, which is momentum per charge, per unit charge dependence. So it's very, very strange. if you do it accurately, helium, carbon, oxygen has one power law dependence followed by another power law dependence. It's, nobody predicted that. Nobody has been able to explain that. Then there's secondary cosmic ray. Secondary cosmic ray, such as lithium, beryllium, boron, are produced by collision of primary cosmic ray with interstellar media, produce boron, beryllium, lithium. An important physics result is that secondary cosmic ray, lithium, beryllium, boron, also have identical rigidity dependence. The three have exactly the same behavior, but are different from primary cosmic ray. And then we have results on carbon cycle, which is the energy source of star. In 1939, Hans Bethe had a paper which earned him the Nobel Prize in '67. It is shown that the most important source of energy in ordinary stars is the reaction of carbon and nitrogen with protons. This reaction forms a cycle in which the original nucleus is reproduced. Carbon interacts with the proton, become nitrogen, and nitrogen beta decays, go back to carbon, interact with the proton, become nitrogen, finally go back to carbon. In the galaxies, what do we measure? Nitrogen over carbon is this value. And the solar system before us has a large errors, but within this error, these two are consistent. What is not consistent is carbon over oxygen measurement in the solar system and measurement in the galaxy. And these two are totally different. Now, let us discuss precision study of cosmic ray through the lifetime of space station. So far, we have measured hydrogen all the way to oxygen. The one in color are primary cosmic ray, the one without color in white are secondary cosmic ray. We are in process to 2024 until the lifetime of space station to measure all the cosmic ray nuclei to hydrogen and to nickel and zinc and beyond. The first is the physics of nickel and zinc. Now, a fundamental question is, are nickel and zinc different from the rest of the primary cosmic ray? Primary cosmic ray up to ion are produced through the lifetime of stars, then accelerated by supernova. Heavy nuclei, nickel and zinc, are produced during explosion of stars. So there are two different sources. The question is, are their properties the same or not? Another fundamental question is, how many classes of cosmic ray exist? I showed helium, carbon, oxygen. A few days ago, we analyzed neon, magnesium, silicon, and shows all the primary, 6 of them behave exactly the same way. Secondary is 3 is the same way, a different way. The major cosmic ray spectrum, whether it's primary or secondary, always show a break at 200 GeV. The fundamental question is there a break for all the elements? And then, more important, why there is such a break? Another question is, how old are cosmic rays? Beryllium-10 decays with a half-life 1.4 million years. Beryllium goes to boron. Precision measurement of the energy of rigidity dependence, beryllium over boron ratio, provide information on the age of cosmic ray. And this is the data, and this is the measurement. The measurement is based on a model, and since we show all the models are wrong, so this result probably is wrong because the model is inaccurate. But with this inaccurate model, you have the lifetime 16.5 plus minus 4 million years. What is more important, we can measure with all the radioactive elements, aluminum, chlorine, manganese, and this will precisely establish cosmic ray as they act within a radioactive cloud. So we now have 4 clouds. We can measure the age of cosmic rays. They better get the same answer. And then this question, another question is, how do cosmic rays propagate in the galaxy? The effective propagation distance is r to the 1/6 times a to the minus 1/3. So you measure different a from 1 to 60, probe different distances. You measure rigidity from 1 to 3000 GeV, probe different distances. So there are 2 different ways to make the measurement. And from this, you can systematically understand how cosmic rays propagate in the galaxies. Another very important question is, does heavy antimatter exist? The Big Bang origin of the universe requires matter and antimatter to be equally abundant at the very hot beginning, because before the Big Bang is supposed to be vacuum. Nothing exists in vacuum. And so the question is, where is the antimatter universe? There are many experiments to search for a reason why antimatter do not exist. This is known as baryogenesis. Baryogenesis will occur if you have a new symmetry breaking. If symmetry doesn't work anymore, you do not have to have antimatter or proton decay. Proton decay experiment is done in 50,000 tons of water with 13,000 photomultipliers. Symmetry breaking has been searched for 50 years, and during this 50 years, many experiments, none has found new symmetry breaking. So no explanation found for the absence of antimatter. No experimental reason why antimatter should not exist. We provide a direct search for antimatter. Matter, a positive charge, bends one way, antimatter bends it the opposite way. So this is the observation of the anti-helium event. This is the bending plan, production bending plan, measurement of velocity. This event have a charge -2. Regular helium have charge +2. The mass of this is 3.81 plus minus 0.3, and this mass is 3.73. So they're exactly the same. The difference is the charge is opposite. Not supposed to exist, but you don't have to listen to it. So heavy antimatter. The rate in MS for anti-helium candidate is less than 1 in 100 million. At this extremely low rate, more data through the lifetime of space station is required to further check the origin of this event. Nobody predicts this exists. Nobody predicts this could happen. So we want to check very carefully about this. So far, we have found no reason why this is not a genuine event. Another physics is solar physics over its 11-year solar cycle until 2024. There are 2 kinds of cosmic ray. High energy cosmic ray goes through the solar system quickly. Low energy cosmic ray trapped in the heliosphere. Now, this is our measurement of proton to helium fluctuation. There is a satellite, Voyager, which after 50 years has left the solar system. They measure proton-helium ratio at extreme low energy, and this is a measurement of AMS. Inside the solar system, Voyager is outside the solar system. Therefore, proton-helium ratio is independent of solar activities. A very important information. We also found out proton and helium, though the absolute value is different, the variation is exactly the same. Between the minimum and maximum is about factor 3. Similarly, for positons and electrons, the absolute value is different, but the variation is the same. And after the solar magnetic field reversal, the characteristics completely changes. So the question is, what is the largest difference over the entire solar cycle? By the end of the space station, we should be able to understand it. An application of AMS solar physics is the radiation protection for man trip to Moon and Mars. And this is a study at NASA. It shows the blue one is the estimated flux, and that was before precision measurement. And since the radiation damage is proportional to Z-square, the effective damage to human being is much larger at iron, as silicon, manganese, and oxygen, much more than protons. This is an estimate. Therefore, it's important to measure the highest Z as a function of time and energy shown over a solar cycle. What is the highest rate? When is the lowest rate? You need to do this before you attempt a trip to Mars, because you need to know during this 11 years what is the safest way to go to Mars. Then you can come back. Space is the ultimate laboratory. It produces particles with energy higher than any accelerator on Earth. Like the Hubble telescope, followed by James Webb telescope, AMS-02 will be followed by AMS-100, proposed in Aachen by Professor Shea. AMS-02 has opened a new field research in physics to study cosmic ray to TV region. AMS-100 will explore all unknown regions up to 1,000 TV with a factor of 1,000 increase in sensitivity. That will be the next step. And this is a sketch of this detector. It's in deep space at a 1 Tesla solenoid magnet can operate without cooling, but the solenoid magnet radius 2 meters, field 1 Tesla. And there's the compensate coil to correct the small galactic magnetic field. It's this 4 meter by 6 meter, this is a calorimeter and silicon tracker. And these are the spacecraft surface module with electronics, power supply, data transmission, data analysis. This is really a super good detector and weighs 40 tons. So the accuracy and the characteristics of AMS-02 data for many different types of cosmic ray require the development of new comprehensive model of the universe. None of our results agree with the current model. Most importantly, AMS will continue to collect data and analyze data for the lifetime of space station. Because whenever a precision instrument such as AMS is used to explore the unknown, new and exciting discoveries can be and has been made. Thank you.
So thank you, Sam, for this excellent presentation. Just one remark from my side. So if we find something which is unexpected, we are developing science. if you do experiments in your lab courses and find something unexpected, something is wrong. Don't mix these two things. Okay, and I guess the comment from the mayor would be, I would like to get a second lecture. Because it's a lot of information in a short time on very complicated physics. So, our next speaker for the evening, Sam introduced him already, it's Bill Gerstmeier from NASA. And I have to tell you, 2 years ago, he was already here, and some of you might have been in the same lecture hall and attended his talk on the future of manned spaceflight. Now, Bill by education is an engineer, and he's one of the few people that I'm aware of which are not taking the decisions from their desk. If you are responsible for human spaceflight in NASA, that's really a huge task. He is the one who at the end has to decide that 2 astronauts go out on the space station and do this repair mission. So 2 years ago he came to Aachen to get a personal impression if this university is worthwhile. And I'm happy that he came to the conclusion we are not doing completely useless things. And that's why we constructed this new cooling system which will be brought to the space station. Now this evening he has 15 minutes to tell us something about human spaceflight, because without humans on space station we will not be able to repair such a complicated instrument like the AMS experiment. Bill, please.
All right, so again, I think you've heard at the very beginning that you need a lot of perseverance and patience to get projects started. Then you get amazing results like Sam just described and told us. And those results are one of a kind. They're really amazing. But they were able to be accomplished on a human spacecraft, a human vehicle called the ISS. And Kirk will talk to you a little bit about that. And then we're going to go ahead and we're going to go do some EVAs, and the crews will talk about that to extend the life of the station. But I think you should also realize that we don't do any of these activities alone. We really do these as a huge international team. And with that, one of the things we're looking at in the US is we're looking at going back to the moon. So I want to show you just a short little video. It's called We Are Going. It's focused a little bit kind of on the US side, but I guarantee you we are not going alone. We are only going if we go with a large international team like we have with AMS. I consider human spaceflight the ultimate team sport. We have to work internationally. We have to work across borders. It takes a tremendous team effort, a tremendous amount of work to move forward. So with that, I'll show you a 4-minute video.
50 years ago, we pioneered the path to the moon. The trail we blazed cut through the fictions of science and showed us all what was possible. Today, our call to explore is even greater. To go farther, we must be able to sustain missions of greater distance and duration. We must use the resources we find at our destinations. We must overcome radiation, isolation, gravity, and extreme environments like never before. These are the challenges we face to push the bounds of humanity. We're going to the moon to stay by 2024, and this is how.
This all starts with the ability to get larger, heavier payloads off-planet and beyond Earth's gravity.
For this, we designed an entirely new rocket.
The Space Launch System. SLS will be the most powerful rocket ever developed.
And with components in production
And more in testing?
this system is capable of being the catalyst for deep space missions.
We need a capsule
that can support humans from launch
through deep space and return safely back to Earth.
For this, we built Orion.
This is NASA's next generation human space capsule.
Using data from lunar orbiters that continue to reveal the moon's hazards and resources, we're currently developing an entirely new approach to landing and operating on the moon.
Using our commercial partners to deliver science instruments and robotics to the surface, we are paving the way for human missions in 2024.
Our charge is to go quickly and stay, to press our collective efforts forward with a fervor that will see us return to the moon in a manner that is wholly different than 50 years ago.
We want lunar landers that are reusable, that can land anywhere on the lunar surface. The simplest way to do so is to give them a platform in orbit around the moon from which to transition.
An orbiting platform to host deep space experiments and be a waypoint for human capsules. We call this lunar outpost Gateway.
The beauty of the Gateway is that it can be moved between orbits.
It will balance between the Earth and Moon's gravity,
in a position that is ideal for launching even deeper space missions.
In 2009, we learned that the moon contains millions of tons of water ice.
This ice can be extracted and purified for water. It can be separated into oxygen for breathing or hydrogen for rocket fuel.
The moon is quite uniquely suited
to prepare us and propel us to Mars and beyond.
This is what we're building.
This is what we're training for.
This we can replicate throughout the solar system.
This is the next chapter of human space exploration.
Humans are the most fragile element of this entire endeavor, and yet we go for humanity. We go to the moon and onto Mars to seek knowledge and understanding and to share it with all. We go knowing our efforts will create opportunities that cannot be foreseen. We go because we are destined to explore and see with our own eyes. We turn towards the moon now, not as a conclusion, but as preparation, as a checkpoint toward all that lies beyond. Our greatest adventures remain ahead of us. We are going.
We're going.
We are going.
We are going.
We're going.
All right, are you going with us? We're waiting for the next instruments to be attached.
So thank you, Bill. Now the next one to talk is the ISS program manager, which is a job which is very difficult. The ISS is to support the astronauts in space, at least that's my understanding. And we have an experiment which is very delicate on the space station, which requires 24 hours, 7 days support. And Kirk Scheidemann managed all this for the past 8 years. It's not trivial to keep such an instrument alive on the space station, and I'm very pleased that he's here today in Aachen. Please, Kirk.
Hello.
Yes.
Hello. Okay. Good evening. It's a pleasure to be here with you. This is my first trip to Aachen, and it's been wonderful. So thank you for having us here, and in particular having me here. I spoke to my wife last night and said I'm here at Aachen University, and I'll be speaking after Nobel laureate Sam Ting and Bill Gerstenmaier. And my wife said, "Well, if you can't be funny, be short." So I'll be short. I did want to tell you a little bit about the International Space Station, and I wouldn't dream of talking to you about AMS since Dr. Ting has already done that, but I will tell you about another experiment, one of many that are going on board the International Space Station. So many of you probably know, but I thought I would show this anyway, the size of the space station. So it's really quite large, over 400 metric tons. It would fill up a soccer pitch easily, 17,500 miles an hour, and orbits the Earth 16 times a day, 16 sunrises and sunsets, over 84 kilowatts of power. So Dr. Ting, we actually have more power for you if you'd like. So, it's a wonderful platform for experiments. It really is all kinds of experiments. And in fact, you've already heard why being outside the Earth's atmosphere makes it a wonderful platform to study particles at higher energies than can be ever done here on the surface. On board today, we have 6 crew members, and you see them here. On the far left, I guess, you have David Saint-Jacques, a Canadian Space Agency astronaut, just like Jeremy you see down there. Anne McLean, Ola Konyenko, Alexei Ovchinin, and Nick Hague. So let me see if I can point to them. I want to show you these two, Alexei and Nick. They are very unique astronauts, cosmonauts. They're the only two who have ever been on a rocket that aborted, survived, and then launched back into space. So on October 11th of last year, Alexei and Nick were on a Soyuz vehicle that aborted. Bill Gerstenmaier and I were there that day. Fortunately, the Soyuz was an amazing spacecraft, separated from the rocket. They landed about 300 kilometers away, and within, I don't know, maybe 3 hours, they were back with us in Baikonur. So really an amazing. And then on March 14th of this year, so October 11th, they launched. The rocket had a problem. They landed back on the Earth, and 6 months later, March 14th of this year, they walked back up to a rocket and got in and flew to space. So amazing individuals and set a new standard for the planet. They're all doing one. Last, Christina Cook, they're on the far right, a U.S. astronaut, all doing wonderful work on board the International Space Station, even as we work here on the planet. About 2 weeks ago, we had a big power failure on board the International Space Station. So I talked about 84 kilowatts. One of our solar arrays sends its power through this box that you just saw. Let's see if I can try that again. It's supposed to loop. Well, that's all right. You saw it. Anyway, it's like a power substation, basically. This sends the power down to the International Space Station, sends it into on a power bus, one of our 4 power buses, and this failed, and it failed on a Monday. In fact, it failed Monday morning, just shortly before we were supposed to launch a SpaceX rocket to the International Space Station. That power bus actually provides redundant power to the robotic arm, which is needed to capture the SpaceX Dragon and berth it to the International Space Station. 3 days later, you saw that video, which was, by the way, very, very sped up. It actually replaced that power box, and then 2 weeks ago today, that SpaceX vehicle launched and was grappled, and now is part of the attached to the International Space Station. One of the experiments, so since I wouldn't talk to you about AMS, I wanted to talk to you about another very interesting payload that's on the International Space Station, Cold Atom Lab. So first of all, the Cold Atom Lab creates Bose-Einstein condensates in space for the very first time. It cools, we've already observed atoms into the 100 nanokelvin, so very, very cold. The really interesting thing about space, one is we believe you can actually cool them colder in space than can be done here terrestrially, and certainly anywhere else. So as far as we know, the coldest place in the universe right now is the International Space Station. The other thing that's really interesting is they persist longer. So you can imagine this cloud of really, really cold atoms. On the planets you can do it, and they persist for just a few milliseconds, and they have to be studied quickly. Here we've already produced them, and they persist for over a second. They believe that they'll be able to achieve up close to 10 seconds of persistence of the condensate. So really a unique opportunity to explore fundamental physics in space that really can't be done here on the planet. So great work is being done. And this is a quite large collaboration out of the Jet Propulsion Laboratory in California, where this is being done. Partnerships. So Bill talked about partnerships and how that's important. The International Space Station, of course, is made up of NASA, the European Space Agency, Canadian Space Agency, Japanese Space Agency, and Russian Space Agency, all together as a partnership. You see the flags from the various countries that are participating in that partnership. It really wouldn't be possible to do all the things that are done in space without the cooperation with all these countries. What we can do together is much, much more than any of us can do alone. So really glad to be part of this international partnership. What we're focusing on board International Space Station, we talked about a couple of experiments today, which would be more in the research area. We're also doing technology development. Bill showed the video about going back to the moon. a lot of the technologies that are required to go to the moon, or I love Dr. Ting's picture with the Martians too. So to go to Mars, also that technology is being developed and tested right now on board the International Space Station. And finally, commercialization. I'm sure you've heard a lot about that. Today, all the cargo that flies up is done by private companies. We actually buy the service. NASA buys the service to launch our cargo, much like having DHL ship a package for you. We're working on sending our crews up on commercial vehicles as well. So we NASA buy the service, and a private company provides the rocket and the spacecraft. I talked about the partnership, but I wanted to give you an idea of really how global it is. Over 107 different countries have been involved in the space station one way or another. So private principal investigators, education, activities, or partnerships. So you can see here around the globe all the countries that have been involved in the space station at one time or another. So here you see some of the commercial activities that are going on board today. This is actually the video of, on the left here, is the first commercial crew demonstration flight. It was a SpaceX vehicle, but flying up to the International Space Station and actually berthing, or docking. On the left, you see the station from the Dragon's view, and on the right, you see the Dragon from looking at the space station. So, really making great inroads in flying commercial crew, flying crew on commercial vehicles. In the photographs, you'll see the upper photograph on the left is a Cygnus vehicle. It's another company, private company, that launches cargo to the space station. The bottom left is the beam module made by Bigelow Aerospace. It's actually a module that was built by a company and flown up and now part of the space station. The other picture is a bone tensitometer that we use in fact, we used here on Tuesday of this week to measure bone density of rodents as part of our biological science experiments. And then on the bottom right, you see pictures of CubeSats. A tremendous number of CubeSats have been deployed. In fact, up until a recent India launch with over 100 at one time. In fact, I think today ISS has launched more CubeSats than any other place. At one time, of course, there was a rocket that launched out of India that launched over 100 at one time, but we're up in the 140 range right now of CubeSats deployed. Here are the two vehicles, the SpaceX Crew Dragon and the Boeing Starliner. Those vehicles are making great progress, and we hope to see our crews flying on those vehicles very, very soon. And last, I wanted to mention we're having an ISS Research and Development Conference. We have one of these every year. All the research that's been done on board Space Station has a chance to go and present some of their results, and we're doing that here this summer in Atlanta. I developed this last night. I thought it would be really great to share with you when the space station flies by. You can go outside, look up. It's very, very bright if you haven't seen it. It's the second brightest object in the night sky, so the moon's number one, obviously. But actually, ISS can be brighter than Venus, so it can be very, very bright. And in fact, you see some of these opportunities almost straight overhead. Those will be extremely bright. Last night, it seemed like a great opportunity. Tonight, maybe not so much. With the clouds and the rain, but hopefully it'll clear up and you'll have a chance to go outside. If not, you can go to the website and see Spot the Station, and you'll, no matter where you are in the world, you'll be able to look and see what time the space station is going to fly overboard. All right, with that, I just wanted to end with one other thought. A few years ago, the space station was having a cooling problem, not really that unlike what AMS is having today. And I had the chance to go to my daughter's school and speak to the students, and so I went there and I talked to the students about the space station and the problem that we were having with the cooling system. And after we got done, one of the students raised her hand and said, "Hey, so am I to understand what you really are? Is you're a plumber?" So, actually, that's pretty good. That is pretty good what we do. So we have a couple of EVAs planned coming up to repair the cooling system on the International Space Station. And I guess if you wanted to, you could call it plumbing. It's very, very complicated plumbing. It's plumbing on a house that was never really designed to be plumbed, certainly in space. But really amazing set of spacewalks coming up later this year to repair this fantastic science instrument. So we're really looking forward to that. And so with that, I'll hand it back, and maybe you can hear from some of our other plumbers. Thank you very much.
Thank you, Kirk, for this excellent presentation. So we are fully aware you are here for the astronauts, so here they are. Chris, Jeremy, please, it's your floor. You don't need any special introduction.
So imagine, if you will, just for a second, that the floor beneath you right now is glass. And beneath that glass is 200 miles of nothing, except millions of cosmic rays, I guess, which we hope to measure. But nothing for 200 miles down to Earth. But it's not standing still. Now imagine beneath that glass you're seeing the clouds and the blue ocean and the brown-green continents move by at 5 miles a second. I'm sorry, I'm speaking in non-metric terms, but it's going by really, really fast. And now, take away your chairs, and you're just sitting there suspended, looking down through this glass, 200 miles to Earth. And now remove the glass. Welcome to your first spacewalk. That's what it's like. And I was asked earlier today, does it get your attention? Is it scary? What's it like when you open the hatch for the first time? And I'll share my first experience with you, and maybe you can answer it yourself. We are in the airlock, which is this small volume on the space station I pointed out, but it's hard to see it on as big as the station is. The airlock is just big enough for 2 people and some bags and some equipment. You climb in this, they close the hatch, and we start depressurizing down. And you get really close to vacuum, and the molecules have a hard time getting out, and it seems to take a little while. So that last pull up on the hatch, right before you open it, there's sometimes a small amount of pressure left over on that hatch. And that was the case on my first spacewalk. I was doing this action to open the door, and I didn't know it, but a straw, you know, like a drink straw that you drink your drink from, had left the trash can back in the space station, managed to float into the airlock, and at the time, right when I was opening the hatch, it was right next to my helmet. And as I opened it, this last little bit of pressure sucked the straw out, and it went shoo, disappearing right down into the clouds. And I remember the Capcom, which is the person on the radio telling us our instructions, hearing some noise, but all I could watch was this drink straw disappear down into the clouds. And it was probably only 10 seconds that I couldn't say anything, but it felt like an eternity. And I had received an email from my colleague, Drew Feustel, right before launch, and all it said, and the title, the subject of the email was, "Loosen your grip." There was no body of the email, that's just what it said, "Loosen your grip." And what he meant was exactly what I was doing at the time watching that straw, was I could have ripped the handrail right out of the space station, because just like you did your first spacewalk with nothing beneath you, that's what I was experiencing. However, it doesn't take long to settle back down, because we do a lot of training and preparation in a large swimming pool, neutral buoyancy lab, about the size of this auditorium filled with water. And we spend so much time in there that it's really a comforting feeling to yourself if you can say, I'm just in the swimming pool. And even though you're in space, it's dark out, the Earth is below you, and you're going by all the continents very quickly, you can quickly gauge your emotions and your feelings and just focus on the handrails in front of you, and that's how I calmed myself down on that first spacewalk, and listen to Drew's email, loosen my grip, and pretended like I was in the pool, then off we go with the task. Now, spacewalks are complicated things, and they're 6.5 hours long. It's impossible for us to memorize all of those actions. We would certainly make mistakes and screw things up if it was just up to our own intuition and memory on what to do. So we have this long choreographed script or procedure on how to operate it. And sometimes we have a little bit of notes on some papers on our wrist, but this procedure is read to us from the control room in Houston. And that procedure is developed through the hard work of a large team of people, and that's exactly what we're doing right now with AMS. We are just finishing about 1.5 or 2 years of this period of time where we're doing step-by-step, many days in this large swimming pool. We also have another neat facility called Argos, which suspends astronauts from the ceiling with this harness inside the spacesuit, and with this you get the effect of zero gravity. And we used to have this only in the up and down direction. We've since added capability and have it in the X and Y direction. So within this metal cage, you have really cool sensation as close as you can at zero gravity. Now the tool and some things are still heavy, but the pool and this Argos facility are amazing tools for us to write and prepare these procedures. So back to the task at hand with the AMS EVA repair. We've been pulling all this information with the engineers, a handful of astronauts, myself, Jeremy, Drew, and Luca, who unfortunately can't be here tonight, but they are launching in July, and we're excited for them to get out there and take care of some of these spacewalks for us. So pulling all this together and writing this procedure is a tricky thing, because you don't really know how long things are going to take. We think it's going to take 5 spacewalks, and we need to have the procedure written in a way that we can stop at multiple periods and end the spacewalk and start again in a few days later to do the second, third, fourth, etc. Now, what are these tasks? What are we actually doing? You heard about the amazing capability of AMS. It has a problem with its cooling system, and that's what the team of folks here at Aachen have worked to get the box, a new cooling pump package, ready to go. Now, the size of this cooling box was limited by the physical size that could fit outside of the airlock hatch. And inside this box, all the plumbing and new parts and computers are packaged in a really creative way. But we can't just take that box right to AMS and plug it in, because there is no place designed and originally to plug it in. It was not thought that we would need to access these places by spacewalking. So there's a series of activities at the beginning of the spacewalks where we have to, I describe it to my friends at home as, imagine you have a minivan and you need to get to a repair inside the middle seat. So we have to remove the back door of the minivan, remove the back seat, pull up the carpeting and the doors, and finally you can get to the equipment that you're interested in. And in this case for us, it's 8 tiny tubes, 4mm metal tubes that we have to cut in the very specific places, and then plumb together the new pump package, and essentially bypassing the old pump cooling system, plumbing it into this new box, and then take all of that and reassemble it back to an operational configuration. So that's essentially what we're doing. And initially, I gotta say, we had some challenges with making these metal tube connections and ensuring that they didn't leak. And that was a real challenge for us. A, for just the action of how do you make that metal connection, but also getting to the access and getting into position to make this connection. I'm really honored and proud to say that, especially at the conclusion of this week, we have a tremendous confidence that we can pull this off, and sometime in early next year we'll have a fully functioning AMS that will last for many years to come. So that's the technical side of what we're doing. I want to talk a little bit more about the space suit itself. The space suit is essentially a one-person spaceship, and I guess I have a cup. There we go, wrong button. I was lasing somebody over there, sorry. In my old line of work, I would have ducked and hid from the laser, but the spacesuit, which you can see, is a one-person spaceship. We have no connection or umbilical providing the life support to the suit. Everything that you need is packaged in the backpack, which you can see right here. It has your oxygen, a cooling system, and a bunch of electronics. We do, however, fix ourselves to the space station, much like a rock climber would be crazy to climb Yosemite or a big rock without a rope, although it's been done. We prefer to be connected. So we have a very short leash that we can fix when we want to stay in one position. However, usually we want to go the distance of the space station, which, as Kirk showed you, fits in the footprint of a soccer pitch. To do this, we have much like a dog leash, basically. It's a retractable leash with a small metal cable in there that allows us to go 85 feet. What's that, maybe 20 meters or something? 20, 25 meters. But that's not as big as the space station. So again, like a rock climber might have to climb a really tall rope, a tall face, but the rope's not long enough, and you might have to switch to a second rope to get to where you're going. We do the same thing. We carry multiple of these safety tethers to get out to where we're going. And that's the case with AMS. It's 2 safety tether lengths away from the airlock. Now you're in your one-person spaceship. You're looking down. You're seeing Earth below you, as I previously described. And there's one sound that you hear that is absolute life. And that's the hum of this little fan inside. You can hear it in the helmet. And as long as you hear that, life is good. You hear people talking and yakking away in the communications headset. But the most important sound to us is the hum of this fan, because that means the spacesuit is operating correctly. We do have a display and control module right in front of our eyeballs that we can get some certain messages and check the health and wellness of our suit ourselves. But we really rely on the experts in mission control to tell us how we're doing with our breathing. We don't want to overbreathe and use too much oxygen. We don't, or have degraded CO2 removal capability. So those are the kind of things, the health and status of the spacesuit, that we can monitor, but the ground is really providing us that information, along with what are the steps of the procedure, as I previously described. So here in the picture you can see 2 people, which I think is me and Luca, coming out. I recognize those feet anywhere, or the smell of them anyway. And the spacewalkers, there's 2 people. We have red stripes on one person, which is the person we call EV1, or the lead spacewalker, and white stripes on the other spacesuits. That's how you can tell who's who. And you come out of the airlock, fix your safety tethers, which I just described, and those are these metal kind of reels. And you can see in this picture there are 2 of them together, and that's what we'll need to get to where AMS is located. You might have to pass some bags out to each other, because as a plumber, any good plumber going to a work site, you've got your toolkit and your bag of 90-degree elbows and whatnot. We do the same thing. We carry those bags with us to where we're going. And in the case of AMS, there is no place to, there we go. There is actually no good handrails, no good place to fix yourself. This is the area of interest, or the mirror side of where we're going. We're actually going on to the other side. But there's nothing to grab onto. So when we come out of the airlock initially, we'll have to put what's called a foot restraint into the robotic arm, climb your feet into this foot restraint, let go of the space station, disconnect that safety reel, and connect it to the robotic arm, and then you start moving through the blackness of space, and the arm, which is really long, has to do a big motion trajectory to get to the position where now we can start working. As you can imagine, with in space, if you don't have yourself if you're not braced up as you do, put effort into something, you could push away instead of the thing being pushed in a direction. So this is what the robotic arm is for, giving us this access. All of that takes time. And for AMS, we're going to remove that cover it's on the other side, and then get down into this. So it creates like a little hole, and that's where we have to reach into an area that's deeper than our arms are long to get in there. So I won't go too deep into the technical aspects, other than getting to these 4mm lines is a real challenge, and that was a collective effort of all the engineers and scientists to figure out just exactly where we're going to get this access. Once the access is gained, now reaching in there required special tools, and we have, as Kurt showed you in the video, things fail on the space station all the time. It's a mechanical system, and that's just the nature of life. And so we have to go repair them. And most of those boxes and connectors and cables are all pretty standard, and we train those over and over, and all of us astronauts are very familiar with that. However, in this case, it required developing of some 25, 29, I think, special tools that allow us to get access into this area where our arms can't reach fully, and to cut these tubes and to make the connectors. Then we build all that back up, cover this area again with a big thermal blanket, and that will be the end of the EVAs, and the folks here can flip the switch and pop the champagne, and off we go. Just a few more things to talk about. You can see the short little tether here that we can fix to any of these handrails once we get to the location where we want to work. I did also want to mention the tertiary safety method of not falling off. The primary are the retractable safety tethers. The secondary is this shorter tether that you use when you get to the location where you want to work. But if you had complete brain lock and forgot to hook both of those things up, we do have a little bit of compressed nitrogen inside this tower assembly that fixes to the back of the spacesuit, and it has some gyros in it. As you tumble away, you turn it on, and it'll stop your rate, and then you can control yourself and point back to where you fell from, and then a little bit of compressed gas to get yourself to arrest that departure rate and come back to the space station. We practiced this in a virtual reality lab in Houston, so fortunately nobody's had to do that for real. That leads me to the place that we just came from prior to here, was a virtual reality lab that you all have called CAVE. Is that a common term? Does everybody here know about CAVE? Just an amazing facility that had the space station model in it in 3 dimensions, and Jeremy and I and all of us here had the opportunity to float around in the virtual environment and see that. So I was just really blown away by that CAVE facility, and it's so super cool. I could go on and on about spacewalks for a long time. The only other thing I wanted to say, maybe we'll have some time for questions, and then Jeremy's going to tell you about other aspects of astronaut life, and that is, how long does it take to get out the door? A spacewalk, as I mentioned, is generally about 6.5 hours long, but that's not the time that you're in the spacesuit. If you just put the spacesuit on like it was a pair of pants and a shirt, it would probably take 20 minutes to do it. However, inside the spacesuit, we in the vacuum of space, we are at an absolute pressure of about 4.3 pounds per square inch, which is equivalent to, in altitude to roughly Mount Everest. And if you're familiar with climbing at all, most climbers of Mount Everest use 100% oxygen. There is a few folks that don't, but most normal people need to breathe 100% oxygen, and we do the same thing inside the spacesuit. However, you are susceptible to decompression sickness if you just go right to that altitude. So we have a protocol of breathing the oxygen at a certain pressure series, and that whole process takes about 3.5 or 4 hours. The point of all this is we wake up in the morning of a spacewalk day, we have breakfast, we use the restroom, and we start this 4-hour process. Then you go out the door for 6.5 hours, and then maybe another half hour of reversing the process to get the helmet off. All of that time you're inside the spacesuit, so there's no food. We have a little bit of water, like a Camelback type water container on our belly to last us for that duration. And spacewalking is tough, challenging work. I like to eat a lot, so the hardest part about spacewalking is not eating for 10 hours. I'm only partially joking, because you feel that energy yourself, your personal energy level drop as the day goes on. So it's really nice to get back inside safely with the satisfaction of the whole team that you pulled off a great accomplishment, and that's what we're looking forward to doing for you, Dr. Ting. So with that, I'll hand it over to Jeremy.
Well, thanks for having me. My name's Jeremy, and I was asked to talk about spacewalking, but Chris did that because he has 6, right, Chris? Chris has done 6 spacewalks. I've done 0 spacewalks, so I thought maybe I'd tell you something that I know a little bit more about. Chris flew to space twice, once on the space shuttle and then once on the Soyuz, and lived there for 6 months aboard the International Space Station. So pretty cool background from him. For me, I'm more in your shoes. Is there anybody in here that's interested in working in the space program or maybe going to space someday? Any of you? Yeah, and that's kind of where I'm at. I've been selected. I'm an astronaut. I'm trained, and I'm still training. And I'm very, very lucky. I'm in a very short line to fly in space. In the next few years, I'm going to fly in space. And my role here on this team is supporting from the ground. So like Chris was saying, it's going to be very complex operations to fix the AMS. And I'm just one of the many, many people on the ground that are going to be helping to deliver the instructions to whoever ends up doing these spacewalks, whether it's Luke and Drew, or if it's some of them are in the future, it could be Chris. We'll see what happens. And I'll be part of that team that's helping with the testing, the development, and working on the spacewalk from the ground. So pretty cool opportunity for me to learn from someone like Chris, who's got all this experience that he's sharing with our team as we get ready to take on this great task. But what I wanted to share with you tonight was just my perspective on human spaceflight. You've had a great intro from all of our speakers tonight, but there's a few things I'd like to kind of point out that I think will apply to you, for those of you that are interested in being part of our team in the future. And so, like those spacewalks Chris has been talking about, these 4 individuals just in the last couple of months have pulled off 3 spacewalks recently, doing maintenance on the space station, swapping out a number of batteries was one of the primary tasks they did. And they worked as a team. All of them going out in different pairs, 2 at a time, with a third person enabling them inside, helping them get ready. And that's very much what our working in the space program is for us, is teamwork. We don't do anything alone. If a person could fly to space by themselves, I'd be there by now. I want to go so bad, I'd have finished it already. But you go as part of a team. And these people have really represented that for us. I was talking to a few folks here earlier, and it seems like there's maybe some interest in well, what do these people actually do on space station when they're not out on an amazing spacewalk? And so to give you some insight into that, A day in the life of an astronaut is completely choreographed by a team, another huge team on the ground, who figures out what are all the things we're trying to accomplish over the next week, the next month, the next 6 months. So they prioritize everything, and then they create a schedule for each one of the astronauts on board the space station. And every day, you wake up and you read your schedule, and you just execute the tasks on there. And it includes a lot of the things that you and I do every day. Of course, you have to take care of your body, you have to have time to eat, you have to have time to wash, brush your teeth. Something that might not be as intuitive that we need really badly in space is time to exercise. So just like we take care of our bodies here on the planet, in space it's much worse for us because you're floating everywhere. And it's super fun to float everywhere, but it's not super great for your body. After 6 months in space, you start to lose your bone density, you start to lose muscle mass. And so we schedule about 2 hours out of every day for astronauts to work out. Whether that be running on a treadmill or doing the equivalent of weightlifting in space. We have like really cool machine that we can simulate weightlifting, do some like big muscle group exercises, like it's called ARED. You can put a bar on your back and it simulates doing squats or deadlifts or bench press, curls. And so you can put a lot of stress on your bones and on your muscles to stay in good shape and allow you to do things like feel good when you get back to Earth afterwards, but also stay in shape to go to do an EVA. And we're also, of course, very interested about this for the things we heard about from Mr. Gerstenmaier. If we're going to go to the moon and onto Mars, we need to learn to be effective at maintaining our health on a long journey to Mars. And so we're learning some really, really cool things on the International Space Station. So exercise is one of them. Of course, it's this crazy laboratory, and it's just like a house or apartment you live in, things break. And so we do have to spend quite a bit of time repairing the space station, not just outside, but also inside. And so that's a big part of the day as well. But then finally, there's the most important aspect of the International Space Station and an astronaut's day, and that is science. It's our school in space. We go there to learn. Just like you're investing all this time right now as students learning. And what you're learning now is going to enable us to go further than we've ever gone before. And that's exactly what we're doing on the International Space Station. And why do we do it there? Well, we simply see things differently in space than we see them here on the planet. Dr. Ting's experiment is a really great example of that, where we can see the cosmic rays differently than you can from underneath the Earth's atmosphere. And that's why we sent it to the International Space Station. We can see fluids differently in space. We see that the body behaves differently in space. We see that there are effects that happens to the astronaut, and then they're similar to aging, like rapid aging while you're in space. But then when you come back to Earth, some of them seem to be reversible, and there are keys and clues there. And you, as students, researchers, you understand very well, maybe more than others, that you can use these opportunities where you can remove variables or create a new constant or change the constant, that you can see things differently. And that's what the International Space Station is all about. And we as citizens of this planet are very fortunate to have this laboratory in space that's been created by great minds and great leadership, that all of us can take our very best ideas. You know, if you're trying to solve a problem that will affect many people, this is often how we select the experiments we send to space. If you can work on a problem that affects many, then that's how we select your experiment, and it can go and it can be done by an astronaut on your behalf and help you with your research and bring some amazing benefits back to humanity. And then actually where you see the astronauts in this image, they're in their bedrooms right there. So there are 4 bedrooms. Oops, sorry. At least I didn't laze you like Chris. These are bedrooms, so like you can see Christina here is upside down, and that's her bedroom. Her torso's in her bedroom, and there's 4 of these around the axial direction of that compartment on board space station, that module. And each one of them has like a little, it's kind of like a coffin-sized bedroom that they can float in. And you have a sleeping bag that you just attach to the wall, and that's where you have your own private space and where everyone sleeps at night. Of course, the Russians have 2 more bedrooms down in the other end of the space station in their module, their primary module. And then this is how we get astronauts to space right now. This is the Russian Soyuz vehicle, and this is the one that Mr. Sharman was talking about, that Nick and Alexei aborted out of. And so this is, I mean, this is not their launch in this photo, but this is what it looked like initially. Just looked like any regular day astronauts going to space until they weren't anymore, and then they were coming home. But, so that's Soyuz. But the reason I wanted to recap a little bit about what we talked about earlier, the Commercial Crew program, is because it really highlights to me how space is changing. And I think for you, this is very, very applicable because it impacts your opportunities in the future. I mean, there's so much change going on right now. I think it affects my flying career, Chris's career, but it certainly has a huge impact on what's possible for you in the future. So right now, there's only one way to get humans to space. But now we live in a world, how many of you have seen these rockets land? It's pretty amazing, eh? It really is something. I remember listening to people maybe a decade ago saying that is not possible. And now we live in a world where rockets land, are refueled and reused, just like an airplane is. And this is just the beginning. Of course, there's a lot more work to be done, a lot to be learned. But this is a really visual example of how space is changing. And so I'm going to show you just quickly here how many vehicles that are being developed right now to take humans to space. So of course, there's the SpaceX Dragon, there's the Boeing CST-100, you heard about the SLS rocket. Of course, on the top of that, we need a capsule, so we have the Orion capsule, built to go into deep space. These are all brand new, and they're happening right now, and they represent rapid change in what humanity is able to do in space. And they also represent a reduction in the cost of access to space. And of course, not lost to many of you, if something's cheaper, are we going to do more or less of it? Of course, we're going to be able to do more of it. And that means great opportunity for young minds like you in this audience today. We talked about Gateway. This is yet another huge challenge for us to set a new goal to go out and push our technology to take humanity out of low Earth orbit now and into deep space again, and then to the surface of the moon, a huge enabler to do that. And I don't know about you, but that gets me really excited. I mean, I love the idea of going to the International Space Station. I'm really excited to go there. But the idea of going back to the moon and again pushing ourselves and setting big goals is really, really exciting for me. And we've all touched on this at some point in our talks tonight, but this is what it really comes down to. Astronauts are just a very visual component of a huge team of people that enables us to do incredible things. I love this picture because it was taken when the space shuttle was docked to the International Space Station, and we had representative astronauts from all of the agencies that are involved in the space station in this photo. In fact, Chris, you're in here. Chris is right in the middle here. There he is. But this is so cool. And Mr. Sharman was talking about looking in the night sky for the International Space Station. How many of you have actually seen it before? That's quite a few, yeah. And if you haven't, you really ought to take the time to go have a look. But for me, it is literally a shining example of what we can accomplish when we choose to work together. You know, from my perspective, building the ISS is one of the most complex things we've ever undertook as a society. And we didn't do it as one country. We certainly did it with the leadership of strong countries with a huge space background, but they carried all of us to join together and bring or create new niche capabilities, bring out the best in ourselves, and to do it together. And we'll learn amazing things from the space station. Amazing science. The AMS is a wonderful example of the things that we will learn from space station. But in my very humble opinion, the greatest thing that we will get from the International Space Station is the knowledge of how to work better together as a planet. And from my perspective, that is the most important thing. So literally a shining example of what we can do when we work together. And you know, Chris, you might touch on this again later in the questions, I'm not sure, but when I've listened to my colleagues who have been to space and come back, it certainly touches them, that perspective of leaving the planet, looking back upon it, and just seeing a country without borders, understanding that we live on this speck flying through space. It's crazy. It's the only place in the entire universe that we have the technology to live on right now. It gives us a sense of ownership of our condition of humanity on this planet, and I think that is the greatest gift that space exploration will give to humanity. So I think I'll leave it there, and we have maybe 20 minutes or so to do some questions. And maybe what I'll do is I'll just moderate it. You've got a panel of incredible people here, so if you've got a question, just raise your hand. I'll call you out. Speak loudly, and then I'll repeat the question. So you can go ahead.
I know, Chris, you had the spacewalk with Luca, and Luca's a European astronaut, so some of us know them. So Luca had this incident of water in his hand, and you helped him out. Maybe you can talk a little bit about this incident, how it happened.
Sure. If you didn't hear the question in the back, he asked, was I a part of a spacewalk a few years ago with Luca Parmitano where we had a leaking spacesuit? And yes, it was in 2013, Luca and I were outside, and we were about 45 minutes into the planned 6.5-hour day, and all of a sudden, Luca had an alarm go off, and it said it was CO2 was high, and we knew that the CO2 sensor was very susceptible to water, but the procedure says, do you feel okay? Is it a crazy reading on the dial? Yes, okay, then just keep going and monitor the CO2 yourself. A few minutes later, though, he started to feel an accumulation of water on the back of his head, and as we were discussing it amongst the two of us with Mission Control, I was a little bit away from him and didn't get the opportunity to see the water for a handful of minutes. And then when I approached and got nice and close, I could see in there about half of a grapefruit of water just jiggling around on the back of his head. But we were very stationary as we were talking, so the water wasn't moving. And since this is a technical audience, I can tell you that it's really the surface tension that's the driving force of water in space. And so because we were static and not really moving, neither was the ball of water. It was just getting a little bigger and bigger, because the problem, we didn't know it at the time, was there was water mixing with his oxygen in a way that nobody ever anticipated. And so as oxygen was filling his helmet, so was water. And the path for that oxygen is up over the back of your head and over your face in an effort to keep a clean water air supply. And he also had a clean water supply there too. And over the few minutes of talking, we quickly realized that it was a problem that we needed to deal with. And I will share with you my personal, I'm sorry this is a longer answer, but that I'm not trying to steal a microphone here, but it's worth describing because it encompasses everything. The story encompasses everything this is why we love working in the space business, solving hard problems and working together as a team, as Jeremy said. So in my mind, what was going through my mind at the time, initially, because we have this procedure that I told you about earlier, and I knew that we were about 30 minutes ahead of the timeline, and it was going to take a few minutes for the ground team to talk about it, and it's no problem because they'll steal 15 minutes of our aheadness, but we'll get it back. And I thought, that's going to be fine, we'll keep going. And then, as soon as he tried to taste it and he knew that the water was really, really cold, that's when my mind shifted from like, oh shucks, we're using up time, to, oh, this is kind of serious, because the sources of water are really that drink bag that I mentioned earlier, or your own urine or sweat. Those are all body temperature. The only way it could be really cold water is if it was coming from the technical water in your backpack. And about the same time, all of us converged on the same answer, is, okay, it's time to end this spacewalk. And Luca then started to go back to the airlock. And I remember very distinctly, we were in this position where those safety tethers that I described previously, much like a dog leash, if you walk two dogs, the dog leashes are going to tangle all up and they're going to be confused. The dog leashes are going to get snarled up. Well, our safety tethers are made in the same way, so we defeat that by routing them in a separate path so they can't get tangled up. The problem with this, however, on that particular day, was that in order for both of us to go safely back to the airlock, we had to take different paths, and I had to go around this side of the table, and Luca had to go around this side of the table, and it was probably the distance to go back from me to Jeremy. That's the distance that we had to travel hand over hand. And all problems can never get really, really good super fast, but they sure can get really, really bad super fast. And that's what was happening right at that moment. Luca started to move, the sun set, and I had this image of Luca's silhouette going around the backside of the space station, and this sinking feeling in myself like, ugh, I need to be with him right now. That's why we're out here together, to work as a team in instances like this. But again, really, really quickly through my brain, I thought, okay, it's okay. If our tethers are going to meet where Jeremy is, if he's not there when I get there, I'll just continue up the other path and bump into him. And I can do that pretty quick. And that's all that went through my mind. Kirk, I did think about just taking my tether and chucking it and thinking, oh, it'll reel itself back eventually, but thankfully for you, I didn't do that. And so Luca is just an amazing astronaut, very, very capable and very confident. And when he left, he was talking normal, we could hear each other, but the motion now, when he started putting motion into his body and the suit, the momentum transferred to the water, and the water whooshed around his face, got in his ears, in his eyes, in his nose, and he's somewhere on the backside of the space station. To hear him talk about the story gives me chills, but he's somewhere on the backside of the space station without those senses, and intermittently could hear as the water sloshed around in his ears. We could intermittently hear him because the water was sloshing around in and around the communication microphones. He ultimately got himself back right as we approached into the airlock, and I remember thinking, my only job in life at this moment is to close the hatch. I didn't honestly care about Luca at the time because there was nothing I could do to help Luca. The only thing I could do to help Luca was close the hatch and open a valve with our crewmates inside the space station. So all of that happened in the matter of 45 minutes. So it happened 45 minutes into the spacewalk, and then additional 45 minutes later, we were done with that whole adventure. And fortunately, all worked out great. Luca got back in, and we subsequently spent, a year and a half trying to figure out the problem and the workaround. In the nutshell, the problem was we thought we were purifying the water after every use of the spacesuit, but we weren't well enough, and crud was building up inside there and got the holes of the pump were blocked up and water backed up in ways we didn't anticipate. So thanks for the question. It was a really crazy day in our history of spacewalking, and since we always learn from something, and now we have new procedures for water in the helmet. Who would have thought you have a whole procedure for water in the helmet? But we do, and we take it very seriously.
Many of the difficulties in the space now is the zero gravity. Is there in the future a way to stimulate the gravity on Earth on the ISS?
So the question was, is there, on ISS there's microgravity, and is there any way to simulate the gravity on ISS? And I'd actually tell you that today there is, and we do it. We just don't do it for the humans. So at one point in time, early in the conception of International Space Station, we were going to build a large centrifuge module, which still wasn't large enough for humans, but you get the idea. It turns out that it's very difficult. You can imagine spinning a large mass. One of the big things that we do, as Chris was speaking, is to anticipate what problems we might have. And so if you're spinning a large mass, one of the problems you might have is the bearings might fail and seize up. If you're spinning a large mass and seizes up, you can put tremendous stresses on the space station. You see these wonderful pictures, and you picture this little rock-solid building like the one we're standing in. But in fact, the ISS is extremely light, very, very flexible. Fragile is probably a better word. What separates these guys from the vacuum of space in many cases is 2 millimeters of aluminum. So anyway, there was a big technical problem. We decided we didn't want to solve that problem. And now we have a smaller centrifuge that we can actually put rodents in, mice, and simulate. We don't typically simulate one gravity, but we do simulate fractions of gravity, and they use it as controls in the research. So you can have microgravity, zero gravity, 1G that you can do terrestrially, and then fractions of that, and see how that affects the phenomena you're studying. So, but we're open to more ideas. If you have a great idea of how we can do something like that and how it would help your research, come see us. We're very interested.
Thanks.
Anyone else? Yeah, right there.
Yeah, thanks. Professor Ting, it's a great honor to be here and meeting here. And as we all know, you were born in a special era in Asia, and you traveled a lot around the world. Do you ever think your scientific work has ever influenced by the outside political or social effects? Or as we know now, there are some competitive approaches from the U.S. to the Chinese government, and we would also like to ask the gentlemen from the NASA, do you think how does that gonna influence and foresee the influence to the political conflicts to the whole space developing for the whole human beings? Thanks.
I can answer this question. I have for nearly 50 years involved in large international collaborations. I have a very clear rule. Working with me, you only do physics. I've never done anything outside my experiment. So I know my ability is limited, so I never get involved in anything outside the experiment.
I would say again, like I showed in the video, human spaceflight really demands all of us to work together, and we get tremendous benefit by working together. I really like Station because if you go look on the outside and you look at the individual modules, they're all protected from micrometeoroids. Small particles can hit Station and penetrate them. But each country has solved that same physical problem a different way. If you look at the shields, the way Europeans have built them, they're different. The Russians have a different set of shielding philosophy, and we do in the US. But all of them still provide the same protection to the crews on the inside for this 2 millimeter thin skin that sits there. And that's what's exciting, is each country can contribute to this great endeavor and work in unique ways, and actually makes us stronger by working together as teams. We cooperate today with the Russians. Our governments are not too friendly. But in terms of us on the space station, we don't see any difference. We're still launching their vehicles. We still work with them daily. We solve these same technical problems. And if you have a challenge that's bigger than you individually or is bigger than your country, I think it really forces you and drives you to work together. And I think it's a really positive thing. So I see tremendous advantage to cooperation. I think we'll do more and more internationally and more cooperation. I expect us to continue to keep working together to go do these things. We're not going to go to the moon. We're not going to go to Mars unless we go internationally. It will not be any individual country. They don't have enough technical capability. They don't have enough willpower and enough funding to do it. We're going to do it internationally.